Hey guys, tonight we're going to do something a little strange and a little beautiful. We're going to zoom so far out of your ordinary life that your worries, your to-do lists, even the edges of your room, all shrink into almost nothing. We're going to float together on the largest scales we know how to imagine and ask a quietly outrageous question. What is the shape of everything? You listen to the soft sounds around you, the faint hum of a fan, maybe a distant car, or just the gentle rustle of your sheets, and then, in your mind, you let the ceiling dissolve. The walls fade, the floor drifts away. Cities become tiny constellations of streetlights. Continents blur. Earth rolls beneath you like a marble wrapped in clouds. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you want, you can write in the comments where you're listening from, and what time it is there, little bright dots of consciousness scattered across the planet, all wondering about the same enormous mystery. Now, dim the lights, and let's ease into tonight's journey together. You drift higher, above the swirl of the Milky Way, until even galaxies begin to look like dust in a sunbeam. At this scale, cosmologists use a different kind of language, less about stars and planets, more about space itself. They talk about curvature, expansion, large-scale structure, and they picture the universe a bit like you might picture the surface of a balloon or a vast, invisible grid. When scientists ask, what is the shape of the universe? They don't just mean, what does it look like from the outside? In fact, there may be no outside at all. They mean, if you could zoom out far enough, smooth out all the little bumps of galaxies and clusters, and look at space as a whole, does it bend? Does it loop back on itself? Is it finite or infinite? Does it have an overall geometry, the way a sphere or a saddle or a flat sheet does? You imagine yourself floating on that smoothed-out cosmos, like a tiny speck drifting over an endless, dimly glowing ocean. In every direction, galaxies are quietly sliding away from you, carried by the expansion of space. You don't feel wind, you don't feel motion. You just see the faint red shift in the light from distant galaxies, a subtle stretching of color that tells you they're receding. Cosmologists build mental pictures to make sense of all this. One picture is the balloon. Sprinkle its surface with dots of ink, inflate it, and the dots drift apart, even though none of them are at the center. Another is a stretchy loaf of raisin bread expanding in the oven, raisins moving away from each other as the dough swells. You can almost smell the warmth of the bread, feel the soft give of it under your fingertips. The dough is space. The raisins are galaxies. The shape is whatever that dough is doing on the grandest possible scale. Underneath these gentle images sits Einstein's theory of general relativity. Instead of treating space as a rigid, unchanging stage, general relativity says that space and time are fluid, dynamic, responsive. Mass and energy tell space-time how to curve, and that curvature tells matter how to move. It's like lying on a soft mattress. Your body makes a shallow well, and a marble placed nearby will roll toward you, following the dip you create. On cosmic scales, the mattress is four-dimensional space-time, and galaxies move along the curves it dictates. In the early and mid-20th century, as astronomers mapped galaxies and watched them recede, they began to realize the universe wasn't static at all. It was expanding. That expansion suggested something deeper. Perhaps the universe has an overall geometry, a large-scale shape that depends on how much matter and energy it contains. Too much matter, and gravity might bend space into a closed shape, like the surface of a sphere. Too little, and it might open into something like a saddle. Just the right balance, and it might be flat on average. You picture three different walks. On a perfectly flat surface, you walk straight ahead forever and never come back to where you started. Parallel lines stay parallel, and the angles of a triangle add up to a neat 180 degrees. On the surface of a sphere, like Earth, walk straight long enough in one direction, and you eventually circle back. Parallel lines can meet, like the lines of longitude at the poles. On a saddle-shaped surface, lines that start parallel drift apart, and triangles can have angles that add to less than 180 degrees. Cosmologists ask, on the largest scales, which of these stories does our universe seem to tell? And how could we possibly know, living on one tiny rock in one average galaxy? The answer is that they turn the entire cosmos into a laboratory. They observe the afterglow of the Big Bang, called the cosmic microwave background, a faint bath of microwave light filling all of space. They map galaxy positions in 3 dimensions, tracing cosmic filaments and voids that look almost like bubbles in foam. They measure how fast distant supernovae recede, and how structures grow over billions of years. You can imagine them as careful cartographers of a landscape they can never leave, using light as ink and time as their ruler. Every measurement is like a soft footstep on the fabric of the universe, testing whether the ground beneath is flat or curved. As you float here, surrounded by imagined galaxies like lanterns in a deep, dark sea, you might feel very small. But there's another way to look at it. Somehow, a species that once navigated by stars over waves and deserts has learned to extend that navigation into space-time itself. Instead of asking only, "Where am I on Earth?" you now participate in a question of staggering scale. What kind of place is all of this? Maybe the universe just loves to repeat patterns. The same curiosity that once traced coastlines and mountain ranges now traces the contours of reality itself. From maps of continents to maps of cosmic microwave background fluctuations, it's the same old impulse, stretched across billions of light years. So you breathe a little slower. The room around you feels quieter. Behind your closed eyes, an invisible grid of galaxies gently expands, and you ride along, weightless, wondering what shape this endlessly unfolding map might truly have. You're still drifting in that dark, quiet ocean of galaxies when 3 gentle possibilities begin to unfold in front of you, like pages of a cosmic storybook. Each one is a different answer to the same question. When you smooth everything out and look at space as a whole, how does it bend? Cosmologists give these possibilities simple names: flat, closed, and open. Plain words for enormous ideas. You start with flat because it's the easiest to picture. Imagine you're standing in a huge, featureless desert at night. The sand stretches out in every direction, the sky is perfectly clear, and you can walk and walk and walk without ever feeling the ground curve under your feet. If you draw a triangle in this desert, using beams of light instead of sticks, the angles will add up to exactly 180 degrees. Parallel beams of light will stay parallel forever. In a flat universe, space behaves like that desert, but in 3 dimensions. On the largest scales, it doesn't curve inward like a sphere, or flare outward like a saddle. This doesn't make it small, though. A flat universe can be infinite, extending forever. Or it could loop around in more exotic ways. Flat just means that, locally, the rules of Euclidean geometry hold. The key idea is that geometry and energy content are linked. In general relativity, the amount of matter and energy in the universe determines how space-time curves. Cosmologists compress this into a single, dimensionless number, often called the density parameter. If the actual density of the universe matches a critical value, the universe is flat. If there's more than that critical density, space curves positively like a sphere. Less than that, and space curves negatively like a saddle. So you slide now into the second possibility, a closed universe. Picture the surface of Earth again, but strip away the trees, cities, and oceans. You're left with a smooth globe. On that surface, there's no edge. You can walk due east forever and never fall off. Yet the total area is finite. In a closed universe, space might behave in a similar way, but in 3 dimensions instead of 2. You imagine floating through this closed cosmos. You pick a direction, any direction, and fire off a beam of light. If you could wait patiently for an inconceivably long time, that beam might eventually come back from behind you, like a message that has traveled around the universe and returned to its sender. The geometry here is positively curved. Triangles drawn on such a space have angles that sum to more than 180 degrees. Parallel lines that start off side by side eventually cross, like lines of longitude meeting at the poles. There's a subtle coziness to this idea, a universe that wraps around itself, without edges, enclosing everything in a finite but unbounded whole. For a moment, you feel what that might be like emotionally. To live in a cosmos where, in principle, every path loops back, and there is no outside to escape to. Maybe the universe would feel more like a gigantic room than an endless hallway. A room with no walls, but still somehow containing all that is. Then the third possibility stretches out before you, an open universe. Here, the geometry flips. Instead of curving in like a sphere, space curves outward like a saddle. You picture a horse saddle under starlight, its surface dipping in one direction and rising in another. On such a surface, if you draw a triangle, the angles add up to less than 180 degrees. Lines that start parallel gradually diverge. In a negatively curved, open universe, space has this saddle-like quality in every direction. It can be infinite, not just in volume, but in the way it encourages things to drift apart. It's as if the very fabric of the cosmos prefers paths to diverge, to separate, to open up new distance. You feel yourself hovering over a vast, rippling saddle of space, galaxies clinging to its curves like tiny lights on a roller coaster track. If you could walk or fly forever, you'd never return to where you began, and there'd be no overall looping back. Flat, closed, open. 3 simple words, 3 different large-scale destinies. In some older pictures of the universe, these shapes were tied directly to the question, will the universe expand forever, or eventually stop and collapse? A closed universe, with enough matter, might one day halt its expansion and fall back in a big crunch. An open universe might expand forever, endlessly thinning out. A perfectly flat universe sat delicately between these fates. Modern cosmology, with dark energy in the mix, complicates that old story, but the 3 shapes are still there, embedded in the equations, waiting to be tested against reality. You might wonder how anyone can tell which of the 3 we live in when we're stuck in one tiny corner. The trick is that light carries geometric gossip. The way distant galaxies appear, the pattern of ripples in the cosmic microwave background, the sizes of known standard rulers out there in space. All of these are influenced by the underlying curvature. It's a little like listening to echoes in a cave. Without ever seeing the entire cave, you can learn about its shape from the way sound bounces around you. In the universe, the echoes are patterns in ancient light, the bending of paths, the way structures form and cluster over time. You close your eyes and imagine 3 universes humming 3 different songs. In the flat one, the melody is balanced, neither drawn inward nor flung outward by curvature. In the closed one, there's a sense of circularity, themes that might someday loop back. In the open one, the tune keeps stretching, never quite repeating, always leaning outward into more and more space. Somewhere, late at night, cosmologists compare data to these songs. They feed measurements into computers, angular scales of microwave background spots, distances to supernovae, the clustering of galaxies. The output is a quiet numerical nudge. The universe looks very close to flat, but for now, you don't need the numbers. You just let the 3 possibilities drift around you like softly glowing shapes. A flat plane, a rounded sphere, a saddle curling away. Each is a different way the universe might tell its story of space and time. And maybe, you think, as you feel your body sink deeper into your bed, the important thing isn't choosing one shape as your favorite. Maybe it's simply marveling that a species made of star-forged atoms can even imagine these options at all. The universe might be flat or closed or open, but inside your mind, all 3 can exist at once, like quiet sketches on the dark, infinite page behind your closed eyes. Maybe the universe just loves to give you choices, even if you can never see the whole picture at once. Those 3 possible shapes, flat, closed, open, float around you like soft sketches on dark paper. And now, you reach for the ruler the universe has already given you, left behind like a baby photo pinned to the cosmic fridge. It's called the cosmic microwave background, the ancient afterglow of the Big Bang. You imagine the universe not as the quiet, thin darkness you see now, but as it was when it was very young, only about 380,000 years old. Back then, everything was hot, dense, and glowing. Space was filled with a bright, almost blinding fog of light and charged particles. Photons could not travel far without crashing into electrons and protons. The cosmos was a glowing, turbulent plasma. You picture it as a kind of cosmic soup, thick and humming, like a hot mist in which light is constantly scattered. If you were somehow there, you wouldn't see stars or galaxies, just brilliance, like being inside a cloud lit from all directions at once. As the universe expanded, it cooled. Slowly, the temperature dropped enough for protons and electrons to combine into neutral atoms. When that happened, photons were suddenly free to travel. The fog thinned. The universe became transparent. The moment when that fog lifted, is imprinted in the cosmic microwave background, or CMB. Those photons have been traveling ever since, for billions of years, stretching into microwave wavelengths as space expands. Now, they whisper past you as a faint glow, corresponding to a temperature of about 2.7 degrees above absolute zero. They bathe the whole sky, everywhere you look. You close your eyes and imagine tuning an old television between channels. The static hiss, a tiny fraction of that noise, in real life, comes from this ancient light. Every point in the sky carries a memory of the universe when it was a hot infant plasma. At first glance, the CMB looks almost perfectly uniform, the same temperature in every direction. But if you map it precisely, as satellites like COBE, WMAP, and later Planck have done, you start to see tiny mottled spots. Slightly warmer, slightly cooler patches, differing by only a few 10,000ths of a degree. You picture the full sky map they produced, an oval of swirling colours, red and yellow for warmer regions, blue for cooler ones. It's like a cosmic weather map, but instead of predicting tomorrow's rain, it records subtle density ripples from 13.8 billion years ago. Those ripples are crucial. They are the seeds out of which galaxies and clusters eventually grew. Where the CMB is a little warmer, the matter was slightly denser. Where it's cooler, slightly less dense. Gravity slowly magnified these tiny variations into the grand cosmic web of today. But embedded in this mottled pattern is something more: geometric information. Think of the CMB as a kind of wallpaper on the inside of a spherical shell around you. The light you see in any direction left the hot plasma at roughly the same cosmic time, forming a distant surface of last scattering. On that surface, there's a characteristic scale, roughly the largest distance sound waves in the early plasma could travel before the fog cleared. This distance acts like a standard ruler imprinted in the sky. Now imagine drawing that ruler directly on the surface of last scattering. In a universe with one kind of curvature, that ruler appears to you as a certain angular size in the sky, like the width of your thumb at arm's length. In a different curvature, the same physical size would look slightly bigger or smaller. So, cosmologists use the CMB to perform an almost magical trick. They measure the angular size of characteristic patterns, those acoustic peaks, the typical hot and cold patch separations, and compare it to what theory predicts for different shapes of the universe. In a flat universe, the geometry is just right for that ruler to appear at a particular angle. In a closed universe, positive curvature tends to make things look larger, like drawing on the surface of a balloon and then stepping back. In an open universe, negative curvature tends to make things look smaller, as if space is stretched. You imagine yourself as one of those CMB photons, born in a glowing fog, scattering again and again, then suddenly released into a newly transparent universe. You have travelled across an expanding ocean of space for billions of years, redshifting, cooling, your wavelength stretching, until you finally land in the detectors of a satellite humming quietly above Earth. Inside that satellite, instruments measure your temperature with exquisite precision down to millionths of a degree. They don't see you as an individual. They see you as part of a pattern, one dot in a grand mosaic. But together, you and trillions of your siblings trace out the faint fingerprints of primordial sound waves and cosmic geometry. The data come back to Earth not as a picture at first, but as numbers, intensities, frequencies, directions. Scientists turn those numbers into a full sky map. To your mind's eye, it looks like a softly coloured egg of ancient weather, blue puddles and red islands floating in an orange sea. From that strange picture, they derive a power spectrum, how strong the fluctuations are at different angular scales. A series of peaks and valleys appears in a graph, each peak whispering something about the density of matter, the amount of dark matter, the density of normal baryons, and yes, the curvature of space. You can almost hear the universe singing. Each peak a note in a chord that tells you about its shape. When missions like WMAP and Planck compared these notes to theoretical models, they found something remarkable. The best fit universe is very, very close to flat. If there is curvature, it's so slight that, within our observable region, space behaves almost perfectly Euclidean on the largest scales. You float there, in your mind, surrounded by this evidence, a baby picture of the universe that doubles as a geometric test. The conclusion doesn't slam the door on closed or open models entirely. Measurements always come with uncertainties. But they narrow the possibilities, like gently tightening a lens until the view sharpens. You let that sink in. Human beings, working with faint microwave whispers from the edge of the observable universe, have managed to say, with some confidence, that space is not wildly curved, that the cosmic desert you imagined earlier is, on average, very nearly flat. Maybe the universe just loves to leave clues in its earliest moments, like a parent tucking a note into a child's lunchbox. Here, it seems to say, in this afterglow, you'll find not only your origin story, but hints about the shape of the road ahead. You feel your breathing slow again. Outside your window, the night might seem empty, but in that emptiness, ancient photons are constantly passing, silent and indifferent, carrying the memory of a young universe and the quiet secret that, as far as we can tell, its grand shape is astonishingly close to flat. And as you drift closer to sleep, you might picture yourself wrapped in that afterglow, like a soft, invisible blanket evidence that the cosmos keeps records, even from its earliest days, and offers them up for anyone patient enough to listen. You're still wrapped in that ancient afterglow, the cosmic microwave background like a faint, invisible mist around you, when the universe hands you something wonderfully simple. A triangle, just 3 straight lines, 3 corners. That's it. On your bedroom floor, on a piece of paper, a triangle is utterly ordinary. If you measure the angles carefully, they always add up to 180 degrees. It's one of those truths you might have learned in school and quietly filed away as obvious, like water is wet or night follows day. But out here, where the shape of the whole universe is in question, a triangle becomes a detective. You imagine yourself standing on an enormous, perfectly flat plane again. You draw a triangle by walking. You start at one point and walk straight ahead for a long, long distance, never turning, never curving. Then you stop, pivot exactly 60 degrees, and walk again. You do this 3 times, closing your path. If you had the patience to measure each corner, you'd find that the angles add up to 180 degrees. On a flat plane, that's always true. Now, the universe gently bends the rules. Instead of a flat plane, picture yourself on the surface of a smooth, perfectly round sphere the size of Earth, or much bigger. You start at the equator and walk toward the North Pole along a straight line on the surface, which in geometric terms is a geodesic, the path that feels like straight ahead when you're not looking at a map. The air is cool, maybe a little thin, and under your feet the ground curves gently. You don't feel the curvature directly. It just is. From the North Pole, you turn and walk back down to the equator along a different line of longitude. Then, at the equator, you turn again and walk along it until you reach your starting point. You've drawn a triangle on the curved surface of the sphere. Here's the strange part. The angle at the North Pole can be, say, 90 degrees. The 2 angles where your path meets the equator can also be 90 degrees each. You've just drawn a triangle with 3 right angles. That's 270 degrees total. On a curved surface, the sum of the angles in a triangle can be more than 180 degrees. The more the surface curves positively like a sphere, the larger that sum can become. You let that sink in like a soft weight on your chest. Something as simple as a triangle can tell you whether you're living on a flat sheet or a curved surface. Now flip the idea. Imagine a saddle. You can picture the leather, the stitching, the gentle dip in the middle and the raised sides. A saddle curves up in one direction and down in another. If you somehow draw a triangle on a perfectly saddle-shaped surface, extending it out to enormous size, you find that the angles add up to less than 180 degrees. This is the hallmark of negative curvature. Triangles are deficient in angle compared to their flat cousins. So, you have 3 subtle tests in one simple shape. Flat space. Triangle angles equals 180 degrees. Positively curved space, sphere-like. Angles is greater than 180 degrees. Negatively curved space, saddle-like. Angles is less than 180 degrees. You can't lace the entire cosmos with ropes and protractors, of course. But the same geometric logic applies. In curved space, the meaning of straight changes. The shortest path between 2 points is still a geodesic, but its behavior and how these geodesics meet, diverge, or converge depends on curvature. You picture space-time as a flexible fabric again. On this fabric, light rays trace geodesics. Galaxies move along geodesics. Even your own path through time is a kind of geodesic, shaped by gravity. When space-time is curved, geodesics that start out parallel can either converge, like on a sphere, or diverge, like on a saddle. The universe, very kindly, offers many kinds of triangles made of light. Imagine 3 distant galaxies, with beams of light tracing between them, forming the sides of a huge triangle. Or picture one galaxy, your telescope, and specific features on the cosmic microwave background as points of a cosmic triangle. On the largest scales, the way light paths bend tells you whether the underlying space is flat or curved. Einstein's general relativity says that mass and energy curve space-time. Near a massive object, like a star or a galaxy cluster, light bends, geodesics twist, and triangles drawn with light can reveal that local curvature. This is gravitational lensing, which astronomers actually observe. Background galaxies smeared and stretched into arcs, like faint fingerprints of gravity on glass. But the question of the universe's overall shape is bigger than local lumps and bumps. It's about the curvature you'd see if you somehow smoothed everything out and looked at the average geometry over enormous distances. Here, your earlier friend, the cosmic microwave background, comes back into view. Those tiny hot and cold spots have characteristic sizes, like the base of a triangle whose apex is your telescope. How big that base looks, in angular terms, depends on the geometry of the space in between. It's like holding out your hand at arm's length. The same hand looks larger or smaller depending on how your eyes and the space between you and your hand conspire. On Earth, you can approximate flatness over small regions. Your desk is flat enough to draw normal triangles, even though you know you're on a round planet. In the same way, space-time can be curved overall, but look almost flat on scales we're used to. Curvature reveals itself when you zoom way, way out. You lift your attention now, in your mind, beyond galaxies, beyond clusters, to a scale where the cosmic web looks like fine, pale threads of light crossing vast, dark voids. Somewhere beyond even this, you imagine placing a cosmic protractor, trying to measure the angles between beams of ancient light. You won't get a neat classroom diagram. You'll get probabilities, error bars, best fits. The real universe is noisy, messy, dynamic. But deep underneath that mess, geometry still whispers its rules. There's something beautiful about this, you realize. You don't need to step outside the universe to ask about its shape. You only need to pay attention to how lines behave inside it, how they converge, diverge, loop, or stay parallel, how triangles close, and what their angles add up to. The same way you can infer Earth's roundness from sailing ships disappearing hull first over the horizon, or from the paths of airplanes curved on a globe, you can infer cosmic curvature from the way light moves and structures align on the largest scales. You feel a strange comfort in this continuity. The geometry that once helped sailors navigate oceans now helps you navigate the universe. The tools have become more sophisticated, the distances unimaginably larger, but the questions are familiar. Maybe the universe just loves using the same simple patterns in bigger and bigger arenas. A triangle on a page, a triangle on Earth, a triangle in space-time, they all tell versions of the same story. As you lie there, perhaps your pillow cool against your cheek, you let yourself imagine that every beam of starlight, every photon that passes through your room, is tracing some tiny piece of a cosmic geodesic. Each one, in its own way, respects the rules of the universe's geometry, whether that geometry is perfectly flat or just nearly so. You may never personally measure an intergalactic triangle or map the geodesics between galaxy clusters, but by listening to the scientists who do, by letting their results flow into quiet images in your mind, you participate in the same act of wondering. What kind of triangle are we all inside of? You exhale slowly, and for a moment, your worries feel like small scribbles in the corner of a much larger sketch. The big shapes, the curves of space-time, the arcs of light, the secret sums of cosmic triangles carry on. Whether you're awake to think about them or asleep and dreaming, the universe doesn't mind either way. It just keeps its geometry steady and patient for anyone who cares to notice. You're still holding that cosmic triangle in your mind when another, quieter question knocks at the door. Even if you knew the curvature, would you really know the shape of the universe? The triangle sighs and steps aside. Topology walks in. You imagine yourself standing once again on that enormous, smooth sphere. You already know it's positively curved. But there's another important feature. Its topology, its overall connectedness, the way space is stitched together. The sphere's surface has no holes, no handles, no tunnels. It's simply connected. You can draw a loop anywhere on it and shrink that loop down to a point without cutting through the surface. Now you shift to a different surface, a donut, or more precisely, a torus. You can feel it in your hands, warm and slightly squishy, maybe still smelling faintly of sugar and yeast. Topology cares about the fact that this shape has a hole. Draw a loop that goes around the hole, and you can't shrink it to a point without tearing through the dough. That's a topological difference. Here is the twist. You could imagine a torus whose surface is perfectly flat locally, like a square of rubber whose opposite edges are glued together. You could live your entire life on that torus, measuring triangles and maybe finding that, on average and on small scales, the curvature is zero. Locally, it feels flat, but globally, the space loops around. Topology is what tells you whether space connects back on itself, whether it has holes or handles, whether traveling far enough in one direction might bring you back to where you started. Curvature tells you how the space bends at each tiny patch. Topology tells you how all the patches are sewn together. You let this distinction settle, like powdery snow on a quiet street. Curvature is like the slope of the road under your feet. Is it tilting up, down, or staying level right here? Topology is the layout of the entire city, whether streets form simple loops, dead ends, or intricate networks where you can wander forever without repeating. In your mind, you zoom back to 3 dimensions. Now you're not on a surface but inside a volume, a 3D space. The universe you inhabit could be curved or flat locally, just like the surfaces you were imagining. But its topology could still be wild. Space could be infinite and simply connected, like an endless plane. Or it could be finite but unbounded, like the 3D analog of a torus, where moving straight ahead could eventually bring you back to your starting point. You picture yourself in a cosmic hall of mirrors. If space loops back on itself in just the right way, light from a distant galaxy could circle the universe and reach you more than once, from different directions. You might see multiple images of the same object scattered across the sky, like reflections repeating between facing mirrors in a dimly lit bathroom. The air in that imaginary hall feels cool, and your footsteps echo softly as you walk, even though you know there's no real floor, no real walls, just space curling back on itself. Physicists often separate the universe's description into parts. Its metric, how distances are measured, its curvature, how those measurements behave in small regions, and its topology, how the whole structure is connected. General relativity, through its equations, tells you a lot about the first 2. But topology is trickier. Einstein's equations don't uniquely fix how space wraps around on the largest scales. So when cosmologists say the universe is flat, they usually mean that, locally and on large scales, the metric has 0 curvature. But that flat space could still be topologically exotic, like that square with opposite edges identified, but extended into 3 dimensions. The difference between an infinite flat space and a finite flat 3 torus is a difference of topology, not curvature. You realize that the question, what is the shape of the universe, has been hiding 2 separate questions all along. 1. What is the curvature of space? 2. What is the topology of space? They sound similar, but they're not the same. Curvature is like asking, is this sheet of paper flat, or is it bending? Topology is like asking, are the edges glued together into a cylinder or a donut, or left loose? You inhale slowly, feeling your chest rise, the fabric of your clothes soft against your skin, and you let yourself imagine that the edges of your own universe might be, not edges at all, but identifications. Directions could wrap around in ways your everyday experience never hints at. There's a playful, almost childlike thought that comes with this. If you had a magical spaceship with unlimited fuel and time, and you pointed it straight ahead, would you eventually come back from behind yourself? Or would you just keep going forever, never repeating, the stars endlessly new? Topology is the part of cosmology that leans into that question. The observable universe, the part we can see, is like a bubble defined by the distance light has had time to travel since the Big Bang. Beyond that bubble, space may continue, but it's hidden from us by the finite speed of light and the finite age of the cosmos. Any topological trickery that happens beyond this horizon is, for now, out of reach. But inside the bubble, there might still be telltale signs. If the universe's topology causes space to wrap around on scales smaller than or comparable to our observable region, we might detect repeated patterns in the sky, the same structures or the same patch of the cosmic microwave background showing up in different directions. You won't chase those signatures just yet, that's for later, but you feel the idea hover nearby, like a lighthouse beam passing over dark water. One of the strangest parts of this story is how normal your day feels compared to the possible weirdness of global topology. You wake up, brush your teeth, answer messages, lie down to sleep. Nothing in that routine suggests that space might be a multi-connected manifold with non-trivial homotopy groups. And yet, mathematically, that's on the table. You smile a little at the contrast. A simple bed in a simple room, floating inside a universe that might be globally shaped like a three-dimensional donut, or a more elaborate structure with names that sound like spells. Poincaré dodecahedral space, for example. Maybe the universe just loves hiding wild mathematics behind very ordinary mornings. There's something comforting in that too. You don't need to understand all the technical language to feel the awe. It's enough to know that, beyond curvature, there's another layer to the question of shape, another dimension of mystery. As you lie there, you can imagine reaching out with your mind and gently pressing on the edges of space, only to find that there are none, just paths that might loop or stretch, connect or not, according to rules written deep into the universe's topology. You may never know for sure which global shape our cosmos has. But simply knowing that the question exists, that curvature and topology are different, that local measurements and global structure aren't always the same, adds a quiet richness to the night. Your own life is a little like that, you realize. Locally, day to day, things might feel flat and predictable, but globally, when you zoom out over years, your path may loop back, cross itself, reveal patterns you didn't see up close. Maybe the universe is teaching that lesson in geometry too, that there's always a larger structure, a deeper connectedness, waiting to be discovered if you can step back far enough. You breathe out, slow and steady, and let the thought go. Somewhere above you, stars drift in orbits, galaxies in clusters, all of them suspended in a space whose curvature we've started to measure and whose topology remains, for now, one of the gentlest and grandest puzzles we can dream about. You're still thinking about topology when the universe offers you something that sounds almost like a joke. What if you live in a cosmic donut? Not a sticky, sugary one, but a three-dimensional cousin of that shape. Mathematicians call it a three-torus. You can just call it the donut universe. To ease in, you start in 2 dimensions. Imagine an old-school video game where your character walks off the right side of the screen and instantly appears on the left. If you fly up off the top, you drop back in from the bottom. There's no true edge. The exit is glued to the entrance. In your mind, you're suddenly that tiny sprite. The screen glows softly in pixelated colors. You walk right, step after step, and nothing ever stops you. The world feels endless, but if you could zoom out and see the code, you'd realize the game world is a finite little rectangle whose opposite sides are identified. That's a flat 2D torus. Take a square, glue the left and right edges together, then glue the top and bottom edges. Locally, it's flat. Triangles still have 180 degrees. Parallel lines stay parallel. But globally, space wraps around. Now, gently add a dimension. Instead of a square, think of a box. You glue the front face to the back, the left face to the right, the floor to the ceiling. Again, locally, if you look around inside, things feel ordinary. You can build flat tables, you can draw standard triangles, you can do Euclidean geometry, and it all works just fine. But this 3 torus is finite. It has a limited volume, and yet it has no edges, no outer boundary you can fall off. If you fly your spaceship straight ahead, you eventually re-enter the same region from the opposite side. If you head up long enough, you drop in from below. You close your eyes and imagine this. You're in a small, cozy spaceship. The control panel glows with soft blues and greens. The engine hums quietly beneath your feet. You point the ship along what you think is a straight line and let it drift. Outside, galaxies slide by like distant lanterns. You pass one particular spiral galaxy, its arms faint and bluish, and keep going. Time stretches, stars come and go. At some unimaginably later moment, You see a spiral galaxy again that looks eerily familiar. Same tilt, same outline of dust lanes. In a donut universe, that might not be a coincidence. It might be the same galaxy, seen from a different direction after light has wrapped around the cosmos. The idea feels like standing in a hall of mirrors. In a rectangular room with mirrors on opposite walls, your reflection repeats over and over, receding into the distance. The room itself isn't actually infinite, but your image appears endlessly because light bounces back and forth between the mirrors. In a three-torus universe, something similar can happen without literal mirrors. Space itself is wrapped, and light can circle around. A single physical object could produce multiple images scattered across your sky. The observable universe might contain clones not of you, but of galaxies, repeated by geometry. You take a slow breath. The air in your room feels still and familiar, but your mind is walking through this multi-connected space where straight lines don't lead to the outside, only back to where they began. The important thing is that this donut universe can be locally flat. All the triangle tricks from earlier still work. If you zoom in anywhere, the geometry looks like ordinary Euclidean space. General relativity is perfectly happy with that. The equations don't forbid a flat universe whose topology is wrapped up like this. So even if cosmologists measure the curvature to be very close to zero, like they do with the cosmic microwave background, that doesn't automatically tell them whether space is infinite or donut-shaped and finite. Curvature and topology remain separate questions. You imagine the cosmic microwave background now as wallpaper not just on a sphere around you, but on the inside of this three-torus. Because space loops, that wallpaper might repeat. The same patch of ancient light might be seen in multiple directions, rotated or flipped, like a pattern in a tiled floor. You picture looking up and seeing the CMB full sky map, soft mottled colours, red and blue speckles. Then you imagine cutting that map into pieces and tiling it across a larger surface. Some edges match perfectly, patterns continuing smoothly from one tile to the next. That's the kind of subtle repetition scientists hunt for in the real sky. You won't dive deeply into the statistics and algorithms here, that comes later, but you can feel the intuition. A donut universe leaves fingerprints of repetition, like a quiet cosmic déjà vu. There's a strangely intimate feeling in thinking the universe might be finite but unbounded in this way. Instead of being lost in an infinite expanse, you'd be living in a vast, self-connecting room, huge beyond anything you can personally traverse, but still, in principle, countable. At the same time, the scale could be so large that you'd never notice the wrapping. If the box of the torus is many times bigger than the observable universe, then all you ever see is a patch that looks indistinguishable from infinite flat space. You'd be like an ant walking on a planet so enormous that every step feels like a stroll on an endless plain. You feel that thought land softly. The universe might be finite, but so huge that, for all practical purposes, it behaves like infinite. And you, lying there in your room, would have no way to tell, except through extremely delicate measurements of patterns in the sky. Maybe the universe just loves giving you questions whose answers are technically knowable, but practically hidden behind sheer scale. Your senses drift inward for a moment. The weight of your body on the mattress, the gentle pull of gravity, the faint texture of the sheet under your fingertips. Everything about your local world feels solid, grounded, edged. Walls, doors, corners. The idea that space itself might not have edges at all, while still being globally finite, feels almost like a spiritual riddle wrapped in mathematics. Of course, a three-torus is only one possible topology. Cosmologists have catalogued many more exotic shapes, spaces built from dodecahedra or from other polyhedra with faces identified according to intricate rules. But the donut universe is the friendliest to picture, a kind of training wheel for the mind. You don't have to adopt it as true to appreciate its beauty. Just letting the possibility live in your imagination for a while is enough to stretch the boundaries of what space can mean. You think back to that old video game screen, your little character wrapping around the edges. As a kid, maybe you never thought about what that implied. It was just how the game worked. Now, you can see it as a small, pixelated metaphor for a very grown-up idea, that your entire universe could be something like that, only in continuous space, with galaxies instead of sprites, cosmic time instead of levels. And somewhere, perhaps, there are researchers late at night, their offices lit by the glow of computer monitors, running simulations of light in a three-torus universe. Watching how patterns in the microwave background would repeat, comparing those patterns to the real sky, listening for the faint echo of a donut-shaped cosmos hiding inside the data. You don't need to know their equations to feel the kindness of that effort. Humans trying to figure out whether the place they live in is wrapped like a donut, stretched out infinite, or something stranger still. For now, as your eyelids grow a little heavier, you can let the donut universe drift past you like a gently spinning ring of stars. Maybe it's real, maybe it's not. Either way, it's a reminder that, when you ask, what is the shape of the universe? You are really asking something incredibly deep. How does everything connect? You let the donut universe spin slowly in your mind, and you start to wonder, if space really wraps around, if it really folds back on itself, how would you ever know? The universe answers, very softly. You look for repetitions in the sky. You're back inside that quiet spaceship now, hovering just outside Earth's atmosphere. Below you, the planet is a dark disk edged with moonlit clouds. Above you, the sky is not black. Not really, it's filled with invisible microwaves, the fossil light of the cosmic microwave background. You imagine turning your ship into a slow scanner. The nose tips up, then down, left, then right, mapping the whole sky. Every direction gets its own tiny measurement of temperature. Warmer by a hair here, cooler by a hair there. The result, once again, is that mottled full sky map. Blues and reds and yellows smeared into a pattern that looks random at first glance. But now, instead of asking only about curvature, you lean in and ask a more delicate question. Does any part of this pattern repeat? If the universe has a multi-connected topology like the three-torus or even more exotic shapes, then the same physical region of space could be seen in multiple directions. The surface of last scattering, that distant shell where the CMB was released, might intersect itself in clever ways, like a folded piece of paper. Where those intersections happen, you'd get circles on the sky that match each other. You picture it like this. Draw a big circle in one part of the CMB map, then draw another circle somewhere else. If the universe loops around just right, the temperature fluctuations along those two circles would be nearly identical, point by point, like two pieces of a jigsaw puzzle that were cut from the same region of a photograph. These are the famous circles in the sky that cosmologists hunt for. You imagine yourself tracing one such circle with your fingertip on an invisible celestial sphere. Around and around you go, feeling the sequence of hot and cold spots like braille under your hand. Then you slide your hand to another part of the sky and trace again. If topology is playing tricks, the two sequences would match same highs, same lows, shifted maybe by a rotation, but clearly siblings. In reality, scientists don't use fingertips. They use algorithms. They feed the full CMB map into computers and let them systematically compare circles of many sizes in all possible orientations, searching for matched patterns. It's like looking for rhyming phrases in a huge, noisy poem, where the poem has been scribbled onto a sphere and smudged by cosmic history. Inside your mind's eye, you can see those algorithms at work. A virtual grid wrapping the sky, circles sliding and overlapping, numbers rising and falling as correlations are tested, rejected, tested again. Somewhere, late at night, a researcher sips lukewarm coffee, while a progress bar crawls forward on a screen full of stars. If the matches were strong, if two circles lined up in a way too perfect to be a coincidence, that would be a whisper from topology. I wrap around. You've seen this place before. But the universe, so far, has been mostly quiet on that front. When satellites like WMAP and Planck provided beautifully detailed maps of the CMB, teams of cosmologists searched for those circles. They tested models of a torus-shaped universe, models based on more exotic manifolds, models where the fundamental domain, the repeating tile of space, was smaller than the observable universe. The outcome was, in a way, its own kind of answer. Strong, obvious circles were not found. If space is multiply connected, its repeating tile must be large, probably larger than the part of the universe we can see, or the topology is subtle enough that its signatures hide beneath the noise and imperfections of real data. You let that result settle. It's not a slam of a door, more like a soft closing. The donut universe is not ruled out completely, but its simplest, most dramatic versions are pushed further beyond reach. repetition can be sought in other ways too. Astronomers can look for repeated arrangements of galaxies, like cosmic constellations, showing up twice, separated by huge distances. They can study the large-scale distribution of galaxy clusters, searching for patterns that would hint at a repeating fundamental cell. This is sometimes called cosmic crystallography, as if the universe might form a kind of crystal lattice on the grandest scale. You picture that crystal now, not as sharp edges and glittering facets, but as a gentle grid of light, galaxies sitting at the nodes like tiny glowing beads. If space were perfectly periodic, those beads would organize themselves with a symmetry that could, in principle, be detected. But again, the real sky is messy. Galaxies are born and die, collisions happen, structures grow in a way that includes randomness. Any underlying topological pattern would be blurred by billions of years of cosmic evolution. Looking for repetition becomes like trying to see the original weave of a fabric that has been stretched, washed, and partly unraveled. You turn your attention back to your own senses, the faint buzz of electronics in your room, the soft creak of the building settling, the rhythm of your breathing. Each sound repeats with tiny variations. The brain loves patterns. It finds them in music, in language, in the way waves crash on a shore. So, it's natural that you'd look up and ask, does the universe itself repeat? Maybe the universe just loves teasing that pattern-hungry part of you. It gives you subtle hints, symmetries in the laws of physics, regularities in atomic spectra, the rhythmic dance of planetary orbits. But when it comes to the larger scale topology, it stays coy. There's also something profoundly human in this search for repetition. If space loops back on itself, then in some abstract sense, your cosmic neighborhood is less anonymous than it seems. Light can circle and come home. Paths reconnect. The universe isn't just a featureless expanse. It has a layout, a structure, a hidden architecture. And even if the current data say, no clear repetitions yet, the act of looking has value. It forces you to think carefully about what you mean by shape, to separate curvature from topology, to imagine spaces beyond the everyday. It turns the night sky from a backdrop into an active participant in a grand geometric puzzle. You imagine future missions, future maps, future algorithms, all peeling back the noise a little more, all asking the same quiet question: have we seen this patch before? For now, as you lie there in the dark, you can let the sky above you be both unique and possibly repeating. Every star you've ever seen is a single point in an immense pattern, and whether that pattern tiles the universe or stretches without repeating, it's still beautiful. You close your eyes and picture two circles in the sky, faint and ghostly, slowly sliding until they overlap. For a moment, their patterns match perfectly, and in that moment, you glimpse a universe that folds back on itself like a gentle loop. Then the circles drift apart again, and you're back in your room, with only the hum of distant microwaves and the steady geometry of your own breathing to keep you company. The universe may or may not repeat itself on the largest scales, but tonight, the simple act of wondering about it is enough to trace a quiet loop inside your own mind, one that begins in curiosity, wanders through stars and statistics, and returns to the soft, familiar darkness of your pillow. You're floating again in that nearly flat cosmos, triangles behaving themselves, circles in the sky keeping their secrets, when another whisper rises from the early universe, a brief, wild moment that may explain why everything feels so smooth and flat today. Cosmologists call it inflation. You can think of it as the universe's first deep, shuddering breath. Close your eyes and imagine a balloon in your hands, still wrinkled and slack. The rubber is cool and a little sticky against your fingertips. You bring it to your lips and give the tiniest puff of air. For a moment, almost nothing happens. Then, suddenly, the balloon swells, its surface stretching rapidly. Those wrinkles smoothed away in an instant. Now replace the balloon with space itself. That's inflation. According to inflationary cosmology, in the earliest fraction of a second after the Big Bang, much earlier than the formation of atoms, or even the cosmic microwave background, the universe went through an extremely brief period of accelerated expansion. Driven by a high-energy field, space didn't just expand. It expanded exponentially, doubling in size again and again in a tiny sliver of time. You picture a tiny patch of the early universe, maybe initially curved, lumpy, full of quantum jitters. Then you watch it balloon outwards so fast that any initial curvature is stretched almost perfectly flat, like the surface of an inflating balloon seen from a very small patch. If you stand close enough to that balloon, the curved surface looks like a flat sheet of rubber. The same thing happens in inflation. Whatever curvature space-time might have had is diluted. As space grows enormously, its radius of curvature grows too, and within the region we can observe today, the geometry appears very close to flat. This helps answer a subtle puzzle called the flatness problem. Without inflation, a universe that's so close to flat today would require almost impossibly fine-tuned initial conditions. Any tiny deviation from critical density in the early universe would have grown over time, making space strongly curved by now. Yet our measurements say the universe is still extremely close to flat. It's like balancing a pencil on its tip for billions of years and finding it still upright. Inflation offers a more natural picture. Instead of starting perfectly balanced, the pencil is laid almost flat by a sudden stretching of the table. The fine-tuning is eased by dynamics. No matter what modest curvature you began with, the exponential expansion drives it toward flatness. You feel that idea as a physical sensation. Roughness being smoothed, bumps being ironed out. You might even imagine your bedsheet being pulled tight at the corners, wrinkles melting into a taut, almost perfectly flat surface. Inflation does something like that to space-time. It also solves another cosmic mystery, the horizon problem. When you look at the cosmic microwave background, you see nearly the same temperature in every direction, across regions of space that, in a simple Big Bang model without inflation, could never have communicated with each other. They're too far apart for light or anything else to have traveled between them in the available time. Yet they're astonishingly similar, as if they once compared notes. Inflation's answer is to rewind the tape. Before the exponential stretching, those now distant regions were close together, well within each other's reach. They could exchange energy, smooth out differences, come to a common temperature. Then inflation blew them apart, like dots on a rubber sheet that suddenly yanked outward. Today they lie on opposite sides of the sky, but they share a synchronized past. You imagine two tiny fireflies glowing in a dark room, close enough to blink in unison. Then, in a flash, the room itself stretches to the size of a continent. The fireflies are now oceans apart, but their rhythm, set long ago, still matches. Inflation leaves another crucial mark. It takes quantum fluctuations, tiny, jittery variations in an early field, and stretches them to cosmic scales. Those fluctuations become the seeds of the density variations we observe in the cosmic microwave background, and later, of galaxies and clusters. You picture a placid lake, almost perfectly still. Then a soft drizzle begins, each raindrop making the smallest ripples. Now imagine that, instead of fading, the lake itself stretches, amplifying those ripples into vast, slowly rolling waves. Inflation is that kind of amplifier, turning quantum noise into the blueprint of cosmic structure. That blueprint shows up in the detailed pattern of CMB fluctuations, their spectrum, their near-scale invariance, their nearly Gaussian statistics. When cosmologists compare inflation's predictions to data from WMAP and Planck, they find a remarkable fit. The pattern of spots in that ancient afterglow looks like the kind of pattern you'd expect if inflation really happened. So inflation doesn't just explain flatness. It also naturally produces the right kind of cosmic roughness. Just enough variation for structure to grow, not so much that the universe collapses into chaos. In your mind, you stand at the edge of that early moment, feeling a strange wind of expansion tug at your clothes, even though there's no air, no sound, no light in the usual sense. Space itself is doing the stretching. Distances double and double again, while less than a heartbeat of cosmic time passes. Then, just as abruptly, inflation ends. The energy driving the expansion decays into particles and radiation, heating the universe in a process often called reheating. From there, the more familiar story unfolds. Expansion slows to a gentler pace. Matter forms, light decouples, galaxies ignite. When you step back from this story, you see why cosmologists sometimes say flatness wins, for now. Observationally, combining the cosmic microwave background, galaxy surveys, and other data, the curvature parameter comes out extremely close to zero. Within uncertainties, the universe appears spatially flat on the largest scales we can see. Inflation provides a natural mechanism for that. It doesn't prove the universe is exactly flat or that inflation happened exactly in any particular way, but it makes very nearly flat the default outcome rather than a miraculous coincidence. You let that phrase swirl in your thoughts. For now, our measurements are limited by the size of the observable universe, by noise in the data, by the difficulty of separating subtle curvature from the effects of dark energy and other ingredients. Future observations might tighten the constraints, or uncover tiny hints of curvature that we haven't noticed yet. Maybe the universe just loves to keep us balanced on the edge of knowing. Enough evidence to sketch a clear picture, enough uncertainty to leave room for wonder. For you, lying here, the details of inflationary models, different fields, potentials, reheating scenarios can fade out into the background. What remains is the simple, almost poetic idea that the smoothness and near flatness of the cosmos today may come from a moment of outrageous stretching, an ancient exhale that turned quantum whispers into galaxies and ironed space into a vast, nearly level stage. You notice your own breath now, slow and even. Air flows in, chest rises. Air flows out, chest falls. Inhale, exhale. The universe, in its first instant, may have had its own version of that rhythm. A sudden, enormous breath of inflation, followed by a long, slow expansion that continues even now, carrying galaxies apart like leaves drifting on a widening river. The river, so far as we can tell, runs straight and nearly flat through cosmic distance. But you know now that this straightness may be the echo of an ancient burst, a memory of the time when the universe decided, in less than a heartbeat, to become unimaginably big. Inflation slowly fades from your mind, like the echo of a distant drumbeat, and you're left again with the shape of space itself. Flatness may be winning in the data, but one idea still hangs in the air, gentle and puzzling. Could the universe be finite, yet have no edge at all? You start with something you can feel. Picture yourself walking along a beach at dusk. The sand is cool beneath your bare feet, a little damp. Waves slide in with a soft hiss, then draw back, leaving thin, foamy lace. Above you, the sky curves overhead, but if you just look around at your immediate surroundings, it feels like a flat strip. Ocean on one side, land on the other. Now, slowly, you zoom out in your imagination. The beach sits on the edge of a continent, the continent on the surface of Earth, which is round. You know that if you could keep walking in one direction, ignoring oceans and mountains, you could eventually circle the planet and return to where you started. Earth's surface is finite. You can measure its total area, but it has no boundary in the fall-off-the-edge sense. You can walk forever and never find a literal edge of the world. That's what finite, yet unbounded feels like. Cosmologists borrow this kind of idea when they talk about certain models of the universe. In a positively curved, closed universe, space itself can be finite in volume, but have no outer wall, no enclosing shell. One of the simplest examples is called a three-sphere, the three-dimensional analogue of the surface of an ordinary sphere, but extended into a higher dimension you don't see. You don't need to visualize all four spatial dimensions at once. Instead, you can lean on the analogy. The two-dimensional surface of an ordinary sphere is finite and unbounded. The three-sphere is the same story, one dimension up. A 3D space that loops back on itself with no edges. Finite, but boundary-free. In such a universe, there's no special center, no privileged middle of everything. Every point is as central as any other, just as every spot on Earth's surface can think of itself as the center of the map. If you fly your imaginary spaceship in a straight line long enough, you eventually circle back to your starting point from the other side, if the universe lasts long enough and nothing gets in the way. You feel into that for a moment, the strange intimacy of a cosmos where every direction is ultimately a path back home. When people first hear finite, they often imagine an edge, a cliff you could fall off, or a wall you could touch. But in general relativity, finite volume doesn't require such walls. The equations are happiest when space is smooth, without sharp boundaries. Finite but unbounded spaces like the three-sphere give you that smoothness. You imagine yourself floating in such a universe. There's no outside. Asking what lies beyond is like asking what's north of the North Pole. The question sounds meaningful at first, but dissolves when you realize the coordinate system simply ends there. North stops. Beyond that, the question doesn't apply. In the same way, outside the universe might just be a phrase without a physical reference. If space is everything that can ever be measured or traversed, then there is no outside in any operational sense. There's just the manifold, the space itself, perhaps finite, perhaps infinite, but self-contained. That realization has a flavor, almost like the feeling of finally understanding a joke that's been confusing you for years. A tiny release in your chest, an exhale. In a closed, finite universe, distances and volumes are well defined. You could, in principle, talk about the total amount of matter, the total number of galaxies, the total energy content, at least at a given cosmic time. There is a whole to speak about, not just an endless stretch. At the same time, finite yet unbounded doesn't guarantee that you personally would ever see the wraparound. The scale of the whole could be much larger than the region light has reached since the Big Bang, the observable universe. Your cosmic horizon might be like a tiny patch on Earth's surface, so small that it appears perfectly flat and edgeless, giving you no direct hint of the globe's finiteness. You picture yourself standing on a soccer field at night. The grass is damp and smells faintly sweet. Fog hides everything beyond the stadium lights. In every direction, the visible world ends in a grey wall. You can't see the stadium, the city, the planet beneath your feet. All you know is the illuminated rectangle around you. That's what the observable universe is like. A bright patch cut out by the finite speed of light and the finite age of cosmic time. Whether the grand field around it is infinite or curves back on itself is, for now, beyond your direct view. The mathematics of cosmology encodes these options in what are called Friedmann-Lemaitre-Robertson-Walker models, solutions to Einstein's equations that describe homogeneous, isotropic universes. Within that family, you can choose different curvatures and topologies. Infinite flat space, finite three spheres, flat tori, and more. The equations don't flinch. They simply tell you how such spaces expand or contract as matter and energy evolve. You might think a finite universe sounds more comforting, tidier, easier to grasp everything contained, no endless abyss. But emotionally, the difference between finite and infinite can blur. For a creature who will never travel even to the next galaxy, both are effectively endless. Both are beyond direct reach. Maybe the universe just loves to remind you that your intuitions, shaped by rooms and roads and coastlines, are not always good guides when you scale up to everything. There's a gentle humility in that. The mind likes clear categories, inside and outside, edge and center, finite and infinite. But the cosmos offers you shapes that twist those categories into something richer. Surfaces with no edges, volumes with no center, spaces that are complete without being enclosed. As you lie there, you might look around your room with new eyes. The corners feel so definite, the walls such obvious boundaries. Yet even here, your experience is unbounded in another sense. Your thoughts drift freely through memories, plans, fantasies. They loop back, repeat, expand, contract. Your mental universe doesn't really have an edge, even though your skull does. Cosmic geometry echoes that paradox. You might live in a space that is entirely self-contained, yet feels, from the inside, like it has no limit. You return, finally, to the simple beach picture. You're walking at dusk. The horizon curves gently, but if you didn't know about spheres and globes, you might still believe in an edge beyond your sight. Centuries ago, many people did. Then, with time, experiments and navigation and mathematics revealed the truth. You live on a finite, edgeless surface. Now, in a similar way, your species sends telescopes and equations to the edge of what can be known, testing whether the whole universe might be another kind of finite, edge-free shape. You don't have that answer yet. Maybe you never will. But the question itself is a kind of light in the dark, a reminder that even as you sink down into sleep, your mind can curve outward, touching ideas that stretch far beyond your tiny patch of space and time. You're still walking along the curved possibilities of the universe. Flat, closed, finite, unbounded, when you notice something else at work. It's quieter than galaxies, subtler than curvature, but over time it reshapes everything. It's called dark energy, and you can think of it as the gentle pressure that decides how fast the cosmic story stretches. For a long time, people assumed that the expansion of the universe, discovered by Edwin Hubble, would slow down over time. Gravity, after all, pulls things together. Galaxies attract one another. Even if the universe never fully recollapsed, the expectation was that expansion would gradually decelerate, like a ball thrown upward that slows as it climbs. You imagine yourself tossing that ball into a clear, cold night sky. It arcs upward, slows, and eventually falls back. A universe with enough matter might behave like that ball, expanding at first, then halting, then reversing. With less matter, maybe it would expand forever, but always slowing, asymptotically approaching stillness. Then, in the late 1990 seconds, something surprising emerged from the data. Astronomers were using Type Ia supernovae, brilliant stellar explosions, as standard candles. These particular supernovae have relatively uniform intrinsic brightness, so by comparing how bright they appear to how bright they should be, you can estimate their distances. Combine that with measurements of their redshift, and you get a kind of expansion history, how fast the universe was stretching at different times. You picture one of these supernovae now, blooming in a distant galaxy. For a few weeks, it can outshine the entire galaxy that hosts it, pouring white gold light into space. Telescopes catch that light, split it into spectra, record its fading glow like a heartbeat on a monitor. When two major teams analyzed many such supernovae at high redshift, they found something unnerving. Distant supernovae were dimmer than they should have been if the universe's expansion were merely slowing. They were farther away than expected. The best explanation wasn't that the data were wrong, but that the universe's expansion had actually sped up in recent cosmic times. The ball had not only slowed, it had somehow started accelerating upward. To make sense of this, cosmologists resurrected an idea that had appeared in Einstein's equations decades earlier: the cosmological constant. In simple terms, it acts like an energy density associated with empty space itself, a kind of uniform pressure that doesn't dilute as the universe expands. You imagine the vacuum not as nothing, but as a very calm something, with an energy that's spread evenly everywhere, like a faint perfume that smells exactly the same in every corner of a room. As space grows, there's more room for this energy, but its density stays constant. The total amount increases with volume. This vacuum energy has a strange property. Instead of pulling things together like normal matter, it pushes space-time to expand faster. In the language of general relativity, it exerts negative pressure, which leads to accelerated expansion. Today, this phenomenon is wrapped into the phrase dark energy. In the simplest models, dark energy is just Einstein's cosmological constant, a fixed energy of the vacuum. In more complex ideas, it could be a dynamic field that changes slowly over time. Either way, it acts on the large-scale geometry of the universe. You picture the cosmic fabric again as a vast, elastic sheet dotted with galaxies. Matter and dark matter pull dimples into the sheet, local wells of curvature. Dark energy, by contrast, is like a very gentle, omnipresent stretch, tugging the whole sheet outward. Over billions of years, the tug wins over the local pulls. This has consequences for the universe's shape story. In the old, simple picture, without dark energy, the global fate and geometry of the universe were tightly linked to its matter density. More than a certain critical density, the universe is closed, will eventually recollapse. Exactly critical, flat and balanced. Less than critical, open and destined to expand forever. With dark energy, that tidy connection loosens. The cosmological constant can dominate the dynamics, even in a universe whose matter density alone would suggest a different fate. You can have a spatially flat universe that still accelerates forever, its expansion driven by dark energy. You can even have a slightly closed or open universe whose ultimate behavior is controlled more by dark energy than by matter. You feel the idea settle like a new layer of fabric over the old picture. Geometry on one layer, energy content on another, with dark energy weaving between them. The standard model of cosmology today, the LCDM model, where L is the cosmological constant and CDM stands for cold dark matter, describes a universe that is very nearly spatially flat, with roughly 5% ordinary matter, about 25–30% dark matter, and about 65–70% dark energy. Dark energy dominates the energy budget, and thus the late-time expansion. You imagine pie charts drawn in soft colors, a thin slice for stars and gas, a larger slice for invisible dark matter, and the biggest slice for the even more invisible dark energy. The part that shines, the part you can see directly with telescopes, is only a slim crescent of the whole. This composition affects how we infer curvature. When cosmologists fit models to data combining the cosmic microwave background, supernovae, and measurements of large-scale structure, they're not just solving for one number, they're fitting for the densities of matter and dark energy, the Hubble constant, the curvature parameter, and more. There's a kind of dance among these parameters. Change one, and others adjust to keep the model consistent with observations. Dark energy introduces what's called a geometric degeneracy. Different combinations of curvature and dark energy density can sometimes produce similar observational signatures, especially in the CMB alone. That's part of why multiple independent probes are needed, to disentangle the roles of dark energy and geometry, to pin down both the expansion history and the shape of space. You picture a knot of strings being pulled in different directions. One string is dark energy, one is matter, one is curvature. Observations tug on the knot from various angles. Slowly, the knot tightens, and the allowed combinations narrow down. In the current best fit models, the curvature parameter is very close to zero, and the dark energy component has properties consistent with a cosmological constant, its pressure to density ratio close to -1. This paints a picture of a universe that is spatially flat or extremely close, and will continue to expand faster and faster, galaxies receding from one another at increasing speed. Far in the future, if this picture holds, distant galaxies will slip beyond each other's horizons. The night sky for any given observer will grow emptier, the cosmic web thinning into isolated islands of matter. On the largest scales, the geometry will still be what it is, but most of it will lie forever beyond any one observer's view. You let that future wash over you like a cold breeze. It's not immediate, not threatening, just deeply, quietly strange. Maybe the universe just loves to write long epilogues, and dark energy is one of the pens it uses. For you, tonight, the important thread is this. Dark energy doesn't just push galaxies apart, it shapes how we read the geometry of the universe. It determines how distances grow with time, how light from distant objects is redshifted, how the cosmic microwave background's features project onto the sky. Without accounting for it, our inferences about curvature would be skewed. Your own life unfolds on scales where dark energy is utterly undetectable. It doesn't change the orbit of Earth, doesn't alter the path of a tossed ball or the strength of your step. Gravity from nearby matter overwhelms it completely. Yet, on scales of hundreds of millions of light years and beyond, dark energy becomes the main character, the quiet force setting the tempo of expansion. You lie there, feeling the much more familiar gravity of Earth holding you against the mattress. It's warm where your body meets the bed, cooler on your exposed skin. Outside, maybe a breeze moves tree branches, or a distant car hums by. None of that hints at the existence of dark energy, and yet your entire local world is embedded in a cosmos whose grand-scale fate it controls. Geometry, in the end, is not just a static property, flat, open, or closed. It's entwined with dynamics, with how the universe expands, accelerates and changes. Curvature and dark energy, matter and motion, all belong to the same sentence. As your eyes grow heavier, you can imagine the universe as a great, slowly swelling sphere of relationships. Galaxies receding, light redshifting, distances stretching. And in the equations that describe that swelling, dark energy appears as a simple, almost innocent term, a constant, a parameter, just a symbol on a line. But behind that symbol lies the future of everything, and another layer of meaning to the question you started with. What is the true shape of the universe, when even emptiness itself has power? By now you've met triangles and donuts, inflation and dark energy. You've floated through toy universes and quiet thought experiments. Now the question drifts back to you in a very down-to-earth way. All right, but what do the actual numbers say? You're lying in the dark, room hushed. A faint glow may be leaking under the door. Above you, far beyond the ceiling, there are satellites that have literally turned the sky into a data set. Millions of temperature points in the cosmic microwave background, millions of galaxy positions, thousands of exploding stars caught mid-flash. You imagine those data as tiny fireflies pinned to an invisible chart, each one a measurement of how space behaves. Start with Planck, the space mission that mapped the CMB with beautiful precision. When cosmologists fit a simple curved universe model using only the CMB temperature data, something curious appears. A mild preference for a slightly closed universe where the curvature parameter omega is negative, a little below zero. Not wildly curved, just gently bent inward, like the faint rounding of a gigantic sphere. You can picture this as a graph with a little bump just to one side of the flat line. It's not a deafening shout, more like a murmur. Maybe a bit closed. But the universe doesn't let you stop there. CMB only fits are entangled with other assumptions, how gravity lenses the CMB, how other parameters shift when you let curvature float. That mild hint for closure sits in a web of correlations. So cosmologists bring in backup. They combine Planck with baryon acoustic oscillation, BAO, measurements, those subtle ripples in the distribution of galaxies that act as standard rulers on cosmic scales. BAO data tell you how distances grow with redshift, providing an independent geometric handle on the expansion history. You imagine galaxy surveys now, vast catalogues where each galaxy is a small dot in three-dimensional space, like glowing embers suspended in the dark. The BAO feature is a slight statistical preference for galaxies to be separated by a particular scale, a faded fossil of sound waves in the early universe. When Planck's CMB data and those BAO measurements are combined, the picture sharpens dramatically. That little preference for a closed universe mostly fades. The joint constraint on curvature settles extremely close to zero. Omega is approximately equal to 0.001 plus or minus 0.00, 2 inches 1, commonly quoted analysis. You can think of omega as a dial where 0 means perfectly flat. Small negative values mean closed, small positive values mean open. That uncertainty of plus or minus 0.002 means that within the part of the universe we can see, any curvature must be extremely tiny, so small that the radius of curvature, if it isn't infinite, is far larger than our observable bubble. In other words, to our best instruments, the observable universe looks indistinguishable from spatially flat. You let that sink in like a slow breath. The floor under your bed feels flat enough for your purposes. The universe, on its own scale, seems to be the same way. Flat enough that any curvature hides beyond your horizon. And Planck isn't alone anymore. There are independent analyses using large-scale structure and BAO data without relying on the CMB at all. They, too, find curvature consistent with zero numbers, like omega is approximately equal to minus 0.04 plus or minus 0.04. Less precise than the CMB plus BAO combo, but still pointing in the same direction. No strong evidence for a curved universe. Newer work continues to push on this from different angles. Strong gravitational lensing time delays, updated CMB reanalyses, fresh BAO measurements from massive surveys like DESI, all weaving together a tapestry where flat LSEDM, the nearly flat universe with dark energy and cold dark matter, remains the simplest, best-fitting story. You imagine a long, polished table with many instruments laid out. CMB, BAO, supernovae, lensing, galaxy clustering. Each one is like a different kind of ruler or protractor. Scientists move quietly along the table, using each tool in turn, checking that their measurements of the universe's shape agree. There are tensions and debates around the edges, of course. Some analyses of Planck data alone once seem to prefer a closed universe. Other combinations of data occasionally lean tiny bits open or closed, depending on modeling choices. New methods examine how assumptions about the sound horizon or dark energy might bias curvature estimates. But when you stand back and look at the whole wall of results, a consensus emerges, soft but clear. Within current errors, omega is consistent with zero. If curvature exists, it's very small, well below the level your everyday intuition would ever notice. The observable universe is, for all practical purposes, geometrically flat on large scales. You might picture that as a cosmic level resting almost perfectly centered, the bubble barely drifting to one side, or as a vast, gently glowing grid of galaxies, where, over billions of light years, Straight lines really do behave like straight lines. How good is good enough here? If omega were, say, 0.1, we'd live in a dramatically curved universe. The allowed range today is more like a few thousandths around zero. That means the radius of curvature, if finite, is at least several times larger than the radius of the observable universe, so large that we're living on a tiny, almost perfectly flat patch of whatever the true global shape is. Maybe the universe just loves giving you enough information to sketch the local picture cleanly, while leaving the global story slightly blurred. You can almost feel the limits in your body. Your eyes see a few kilometers on a clear day. Telescopes see billions of light years. But even they are bounded by the finite age of the cosmos. Light has only had so long to travel. Beyond that horizon, the universe could continue flat, curve back, twist topologically in ways you've imagined in earlier sections. Current measurements simply can't reach there. So when people say the universe is flat, what they usually mean is more nuanced. As far as we can tell, within the region we can observe, the spatial curvature is extremely close to zero, consistent with a flat FLRW model, given our assumptions and current data. Not quite as snappy as the universe is flat, but more honest. Lying there, you might feel a kind of strange comfort in this precision mixed with humility. Humans have managed to measure the geometry of the universe to better than 1 part in 1,000, using ancient light and the positions of galaxies, and yet they still say, softly, we don't know the global shape for sure. It's the same mixture you live with every day. You know enough to walk across a room in the dark, but not enough to predict every twist of your life. Local certainty, global mystery. You breathe in, hold it, and breathe out. Somewhere above you, data archives sit on spinning disks in quiet servers, maps of the microwave sky, catalogues of galaxies, light curves of supernovae. Together, they form a record of the universe's attempt to tell you, in numbers, I am almost flat, where you can see me. The rest, the part beyond the horizon, beyond current precision, is still open. And that openness, rather than being frightening, can be something you rest inside, like a vast room with the lights turned low. Maybe the true shape of the universe is exactly flat. Maybe it's only nearly so, curving ever so gently out beyond what you can see. Either way, tonight, the floor beneath you is steady, the laws you rely on are reliable, and the cosmos, on the scales you can test, is a calm, almost Euclidean place. You can let the error bars cradle you like a soft blanket. Not total certainty, not total ignorance, but a warm, honest in-between. Up to now, you've been asking about this universe, its triangles and donuts, its dark energy and almost flat geometry. The question has been big, but still singular. One cosmos, one shape. Now your mind drifts a little farther, as if someone gently nudges the zoom-out button again. The stars you've been thinking about grow small. The entire observable universe shrinks to a faint bubble of light, and you find yourself wondering, in the soft dark of your room, what if there's more than one bubble? You're still lying there, the sheets a little warm where your body rests, the air cool on your face. Somewhere down the hall, a pipe clicks, or a fridge hums. Everyday sounds from a single world. And yet, theorists have dared to ask whether our universe might be only one region in a much larger multiverse, a bigger structure in which many universes, perhaps with different properties, are born. None of this is established fact. It's like a trail that begins in solid pavement, general relativity, quantum field theory, inflation, and then fades into mist. But it's a mist many physicists have chosen to walk into. One path to the multiverse comes from inflation itself. Earlier, you pictured inflation as a single burst, a swift exhale that smoothed and flattened our universe. But some versions of inflationary theory suggest it might be eternal to the future. Quantum fluctuations could cause inflation to end in some regions while continuing in others, like patches of a field of dandelions going to seed at different times. You imagine a vast, dark meadow. In some patches, the seeds have already burst, drifting down and settling into quiet plants. That's where inflation has ended, and normal Big Bang-like expansion takes over. In other patches, the seeds are still tightly closed, inflation still roaring, space still blowing up exponentially. Each region where inflation ends becomes a bubble universe, a pocket of space with its own hot Big Bang, its own cosmic microwave background, its own galaxies. Between the bubbles, inflating space keeps stretching, so the bubbles rarely, if ever, collide. The result is a multiverse, countless bubbles, each internally like a universe, embedded in a larger, inflating background. Inside your own bubble, you might never see the others. The cosmic horizon limits you just as before. But on the whiteboard of theory, many universes now dot the page. A different path to more than one comes from higher dimensions. So far, you've treated space as three-dimensional left-right, forward-backward, up-down, with time as a separate, flowing dimension. But in certain theories aiming to combine gravity with quantum mechanics, like string theory, extra-spatial dimensions appear, usually unseen, because they're curled up or warped in ways that hide them from ordinary perception. You picture a garden hose lying in the grass. From far away, it looks like a simple one-dimensional line. An ant walking along it can move forward or backward, and that's all you'd notice. But if you move closer, or if you are the ant, you see there's another direction, wrapping around the hose's circumference. From the ant's perspective, space has one long dimension and one tiny, circular one. The world is effectively higher dimensional, but one dimension is compactified, too small for big creatures to notice. In some string-inspired models, our 3D universe is like that hose, extended in 3 dimensions but with additional dimensions wrapped up on scales far smaller than an atom, their geometry influencing the types of particles and forces that can exist. You imagine those hidden dimensions as intricate little curls attached to every point in space, tiny, folded rooms you can never enter, but whose shapes quietly dictate the rules of your reality. In yet other scenarios, our universe might be a kind of brain, a 3-dimensional membrane floating in a higher dimensional space called the bulk. Particles and forces like electromagnetism might be confined to the brain, while gravity can leak into the extra dimensions. Here, the image becomes almost tactile. You're lying on a vast invisible sheet. The brain, while above and below you, stretches a larger, unseen volume. There could, in principle, be other brains parallel to ours, other universes with their own matter and light, drifting in the same higher dimensional bulk. You can't see them. Your light doesn't cross the gap, but gravity might feel them faintly, like a whisper through the fabric. All of this sits in a speculative zone, not fantasy, but not confirmed science either. These ideas are attempts to extend known theories into regimes where they might solve deep puzzles. Why particles have the masses they do, why dark energy has its tiny value, why our universe seems so hospitable to complex structures and, eventually, to life. Some physicists go further and suggest an anthropic perspective. In a multiverse where different regions have different physical constants, it's not surprising that you find yourself in a bubble where those constants allow galaxies, stars, and living beings. In bubbles where the constants are wildly different, no observers arise to ask questions. Maybe, they say, the shape and content of this universe are partly selected by the simple requirement that someone can exist inside it to notice them. You might feel a mix of awe and discomfort at that thought. The idea that your existence is a kind of filter, that you're automatically in one of the rare regions where reality is gentle enough to build atoms, stars, chemistry, and brains. Maybe the universe just loves to generate possibilities, and you're in one of the few that happens to look back. Still, it's important to remember, as you drift towards sleep, that these multiverse and higher dimensional ideas are not things we've directly seen. They're like reflections glimpsed in the polished surface of our current theories, plausible extensions of mathematics that fit some puzzles, but haven't yet given us a smoking gun, testable prediction that uniquely confirms them. For now, your telescopes see one observable universe. Your experiments, your everyday life, take place on one apparent 3D stage. The true shape of the universe might include extra dimensions and sibling universes, or it might not. The equations are suggestive, but the data, so far, are quiet. And yet, letting your mind rest for a moment in these possibilities can change how this universe feels. Suddenly, your flat or slightly curved cosmos isn't an isolated object, but maybe part of a larger structure, like a single page in a very thick book. You may never read the other pages, but knowing they might exist changes the flavor of the story you're in. You listen to your breathing, slow and even. You feel the pull of gravity, the warmth of your body, the coolness of the air. Everything you sense is anchored to this universe, this brain, this bubble. The multiverse, if it exists, is utterly silent as far as your nerves are concerned. Still, the fact that your mind can even entertain the idea that it can stretch beyond 3 dimensions, beyond one universe, beyond the visible bubble, says something remarkable about the kind of structures this cosmos has produced. You began by asking about shape: flat, closed, open. Now, that question has unfolded into a larger one. What if the true shape of reality includes layers you can't yet see, extra dimensions, endless bubbles, other brains? There may never be a definitive answer, but tonight, the possibility itself can be a kind of gentle lullaby. The sense that even this enormous universe might be part of something larger, more intricate, more mysterious than you can yet imagine. And somehow, right now, in a small room, on a small planet, in one shining bubble of space-time, you get to wonder about all of it before you sleep. You've drifted through inflation and multiverses, donuts and spheres, dark energy and microwave afterglow. Now the camera quietly zooms back in. The universe shrinks, in your mind, from a web of galaxies to a single spiral, to a single star, to a single planet, to a single room, to a single person, lying in the half-dark, listening, breathing. Your eyes are closed, but behind your eyelids, neurons fire in intricate patterns, tiny electrical storms in a soft, quiet skull. Those storms are made from atoms forged in stellar cores, heavy elements blown out by ancient supernovae and folded into clouds that became your world. Factually, physically, you are a small clump of the universe that has folded back on itself and started asking questions. You flex your toes under the blanket, feeling the fabric brush your skin. You notice the weight of the covers, the slight pressure on your chest. Your body is only about 2 meters long, maybe less. Your reach, when you stretch out your arm, is less than a meter. If you walk outside tomorrow and look up, your naked eyes will see perhaps a few thousand stars at most. And yet here you are, contemplating the shape of everything. There's something almost comical about that. For most of human history, people navigated a very local cosmos. The universe was the land they could walk, the river they could follow, the mountain whose peak they might never climb. The stars were fixed lights. The sun rose and set on cue. The idea that the Earth itself might be round took time to settle in, and longer still for the notion that the Earth orbits the sun, not the other way around, to be accepted. You imagine an ancient sailor standing on the deck of a wooden ship. The boards creak underfoot. Salt air stings his nose. In the distance, another ship slowly disappears, hull first, over the horizon. That's one of the earliest, simplest proofs. The world is curved. The line of the sea itself is telling him that he lives on a sphere. Centuries later, telescopes turn upward. Galileo aims glass at the sky and sees moons orbiting Jupiter, phases of Venus, mountains on our moon. The night stops being a flat ceiling and becomes a layered, physical space. A few hundred years after that, Hubble uses the brightness of Cepheid variable stars to show that the spiral nebulae in the sky are not clouds in our own galaxy, but entire galaxies far beyond. Your mental image shifts. The Milky Way becomes a single swirl among many, like a tiny hurricane in a vast satellite image of storms. The scale of everything keeps expanding. In the 20th century, general relativity adds another twist. Space and time are no longer rigid. They curve and stretch. Suddenly, it's not just that you live in the universe. You live inside a geometry that can be curved, finite, infinite, expanding, accelerating. The question, what is the shape of the universe, only makes sense at all once that idea is on the table. There's a factual chain here. Careful observations, mathematical theories, experiments repeated, cross-checked, refined, from Eratosthenes measuring Earth's circumference with shadows, to Hubble plotting galaxy redshifts, to modern teams calibrating space telescopes. You belong to a species that learns about the shape of reality by asking nature the same question, over and over. What happens if I measure this? You imagine Eratosthenes' sunlight, sharp and bright on an ancient Egyptian well, and then imagine the faint microwave glow in a Planck detector. 2 forms of light, 2 wildly different experiments, both tracing curves, one of Earth, one of the cosmos. And where are you in this long story? You're in a small room, probably with a phone or laptop not far away, listening to a voice trace lines from your pillow to the edge of the observable universe. You haven't launched satellites, you haven't solved Einstein's equations. But the strangely democratic thing about cosmology is that once the data exist, the meaning of them is available to anyone who's willing to listen and imagine. Your ears catch the words flat, closed, open, but your brain turns them into images: deserts, spheres, saddles, donuts, bubbles. You don't see curvature itself, you see metaphors. And that's okay. Every scientist you've ever heard of started there too, using pictures and analogies to make sense of equations. Maybe the universe just loves using small, fragile brains to hold very large, abstract shapes. There's a paradox in your situation. On one hand, you are inconceivably tiny compared to the universe. On the other, you are one of the few known structures in it that can represent the universe internally, as a model, a story, a mental map. A galaxy can't imagine the shape of the cosmos. A black hole can't sit and contemplate its own horizon. But you can. Right now, as you lie there, your brain is quietly simulating possible universes: flat planes, closed loops, infinite saddles, nested bubbles. Each simulation is just patterns of activity in about 1.5 liters of neural tissue, weighing roughly 1.3 kilograms. Cells talking to cells, ions crossing membranes, chemical gradients shifting. Factually, that's all that's happening, and emotionally, it feels like the whole universe is turning slowly in your hands. There's a sensory gentleness in that realization. You feel smaller, yes, but also oddly more connected. The same physical laws that bend space-time also govern the chemistry of your synapses. The same quantum fluctuations that may have seeded galaxies also set the behavior of the atoms inside each neuron. You are not separate from the universe whose shape you're trying to understand. You are a local pattern in it, temporarily awake. You picture, for a moment, the entire observable universe as a glowing sphere dotted with galaxies. Then, in that mental picture, you zoom down into one spiral arm of one galaxy, into a yellow star, onto a small rocky planet, into a city, into a building, into a room, into the person in that room, whose mind is holding the entire sphere as an image. The universe folds back on itself that way, the whole contained as a model inside one of its parts. Humans have built tools to help with that folding. Telescopes are extended eyes. Computers are extended memory and calculation. Scientific collaboration is extended thinking, spread across thousands of minds and decades of time. You might feel alone in your room, but the ideas flowing through your head are collectively built, assembled by countless scientists, writers, teachers, engineers. Your body is small, but your conceptual reach is supported by this entire invisible network. It's like standing on the shoulders of a giant made of many people, stretching back through history. Sometimes it's easy to feel that vastness as a pressure. So many things to know, and you are just one person, tired at the end of a day. But tonight, you might choose to feel it as permission instead. You don't have to solve the universe. You get to visit it in your mind. Like walking through a museum after hours, lights dimmed, exhibits softly glowing. You wander past displays labeled CMB, curvature, dark energy, topology, multiverse. You pause, look, feel what each one evokes, then move on. No test at the end, no grade. Just the quiet experience of being a small, curious thing in a very large, patterned reality. Maybe the true shape of the universe isn't just a question about geometry, but also about perspective. From far away, everything looks like smooth curves and averages. Up close, it's a tangle of specific lives, specific rooms, specific breaths taken in the dark. Your life is one of those tiny details. As you feel your eyelids grow heavier, you might hold both truths at once. You are very small. You are also, in this moment, a place where the universe becomes aware enough to wonder what shape it has. Somehow, both of those can be true, and together they make the night feel both bigger and kinder. You're still there in the dark, a small body in a big universe, when another quiet realization surfaces. You don't just measure shapes, you prefer them. Your brain loves patterns the way your lungs love air. It can't help it. You notice it first in the simplest things. Stare at the ceiling long enough, and your mind finds shapes in the bumps, faces in the shadows, animals in the random texture of paint. Look at clouds, and suddenly there's a dragon, a ship, a heart. Close your eyes and press gently on your eyelids, and strange coloured forms dance behind them. Circles, ripples, flickering lines. This isn't a glitch. It's how you're built. From the first days of life, your visual system hunts for edges, contrasts, contours. Neurons in your eyes and brain are tuned to lines and corners, detecting where one region ends and another begins. Higher up, other neurons respond to more complex patterns, curves, faces, motion. Your perception is a layered process, constructing objects from raw light. You can feel this, in a small way, by looking at an optical illusion. Two lines of the same length can look different if you add arrowheads pointing in or out. A set of dots arranged just so becomes a cube in your mind, even though no cube is actually drawn. Your sense of what's really there is shaped by your brain's hunger for simple, coherent forms. You imagine your mind like a spotlight sweeping across the world, constantly trying to tidy it up. Oh, that's a circle. That's a line. That's a face. That's a pattern I've seen before. Randomness makes it restless. Order makes it relax. Now you bring that spotlight back to the cosmos. When you hear universe, your brain often reaches for simple shapes. A sphere, a flat sheet, a donut, an infinite plane. These images are comfortable. They're easy to picture, easy to rotate in your mind. A round globe, a straight line, a looping circle. Your brain has been practicing these since you learned to draw. So when cosmologists talk about a closed universe, you imagine a sphere. When they mention a flat universe, you see an endless plane. When you hear about a torus, you think of a donut. These shapes are not the full mathematical truth, but they're good enough for your pattern-hungry mind to grab onto. There's a factual reason for this, too. In physics, systems often settle into simple, symmetric configurations because those are the ones that survive. Spheres minimize surface area for a given volume. Planets, stars, and droplets of water all tend toward roundness under their own gravity or surface tension. At the atomic level, orbits and fields fall into canonical shapes, described by simple equations. You look up at the night sky and see circles everywhere. Planets, stars, halos, orbits. You look down at your coffee and see a circular rim, ripples spreading outward like expanding rings. Even in mathematics, circles and lines play a central role, so much so that when you ask, what shape is the universe, it's almost inevitable that your mind frames the answer using those same beloved forms. Maybe the universe just loves repeating its favorite motifs, from raindrops to planets to models of space-time. But there's also a trap hidden in this love of patterns. Your brain is so eager to find simple stories that it can mistake them for reality. It prefers clean categories, flat versus curved, finite versus infinite, multiverse versus not, when the truth may be layered, fuzzy, or somewhere in between. In cognitive science, people talk about heuristics, mental shortcuts your brain uses to make quick judgments. They're efficient, but not always accurate. One of them is the tendency to prefer simple, coherent narratives over complicated, uncertain ones. A flat universe with a clear picture is more satisfying than approximately flat within current error bars, with unknown global topology. You can feel this in yourself. The universe is flat is a sentence you can hold in one breath, a neat, closed circle. The observable universe is consistent with spatial flatness to within a few parts in 1,000, but its global topology remains unconstrained, is less breath-friendly. Science communicators, teachers, and even scientists talking to each other often use metaphors and simplified stories because they fit better into human minds. Balloons, raisin bread, rubber sheets, donuts, these are not literal descriptions of space-time, but they're close enough in certain ways to spark understanding. You imagine a science communicator as a translator, standing between the equations and your imagination. In one hand, they hold tensor calculus and data tables. In the other, they hold desert plains, spheres, saddles, and circles in the sky. They try to map one to the other without losing too much truth along the way. But translation always leaves something out. The true mathematical shape of the universe, if we ever pin it down, will likely live in spaces and concepts far beyond simple 3D objects. It may involve higher dimensions, non-trivial topology, subtle curvature that only shows up in precise statistics. No single metaphor will capture all of it, and that's okay. Your mind doesn't need to grasp every detail to feel the awe. It only needs enough structure, enough pattern, to hang its wonder on. You think about the circles you met earlier, circles in the CMB, circles on spheres, loops in torus universes. Circles are simple. Mathematically, they're just points at a fixed distance from a center. Emotionally, they feel like cycles. Days, years, heartbeats, habits. You return to the same path again and again. Lines, on the other hand, feel like stories. They have direction, a sense of before and after. The universe itself is a mixture of both. Cyclic processes, stars born and dying, elements recycled, and one-way arrows, expansion, entropy increasing. Your mind likes to turn these into narrative shapes, loops or journeys, circles or arrows. So, when you ask, what is the true shape of the universe? Part of what you're asking is this story a circle or a line? Does it loop back in some way, finite, closed, repeating? Or does it stretch on without end, open, infinite, never returning? The data, so far, lean toward an almost flat, possibly infinite or very large universe, one where your observable patch is a small piece of a much bigger whole. But emotionally, you're still drawn to both possibilities. The comfort of a loop, the thrill of an endless line. Maybe the universe just loves giving you questions whose answers are both mathematical and personal. On the cognitive side, researchers studying perception and reasoning find that humans are quick to see structure in randomness, to assume patterns persist, to fit new facts into familiar shapes. On the cosmology side, researchers carefully try to strip those instincts away, forcing themselves to look at the raw data, the error bars, the alternative models. In a way, science is a long conversation between your love of simple stories and reality's refusal to be completely simple. You feel that conversation playing out inside you right now. Part of you wants a neat ending. The universe is definitely X-shape. Another part of you recognizes the beauty of not knowing, of living inside an unfinished draft. So tonight, as you lie here, you might give yourself permission to hold both the stories and the uncertainty, to enjoy the metaphors, balloons, donuts, circles in the sky without mistaking them for the whole truth, to let your pattern-loving brain do what it does best, while remembering that the universe may be stranger, subtler, and more intricate than any single story you tell about it. You can feel the mattress under you, firm but soft, like a surface whose curvature you don't really question. You can feel your breath repeating in cycles, and your thoughts moving in lines. Forward to tomorrow, backward to yesterday, outward to galaxies. In those simple shapes, circles of breath, lines of thought you're practicing, in miniature, the same pattern making that led you to ask about the shape of everything. And maybe that's the quiet secret. The true shape of the universe is not just out there in geometry and data. It's also in here, in the ways your mind turns chaos into pattern and silence into story. Before sleep, you're lying there now with almost the whole story on the table. Flat or curved, open or closed, finite or infinite, simple topology or something far stranger. And the quiet, honest truth is, you still don't know the true shape of the universe. Not completely, not perfectly, maybe not ever. Cosmology, like any science, has built-in limits. One is the horizon. Light has only had 13.8 billion years to travel, stretched by expansion into a bubble of visibility. Beyond that, there may be more of the same, or something different, or nothing at all, but no signal has had time to reach you. Your measurements, no matter how clever, are always drawn on that finite canvas. Another limit is something cosmologists call cosmic variance. On the very largest scales, there just aren't many independent regions to compare. You only get one observable universe, one set of long wavelength patterns in the cosmic microwave background, one realization of the cosmic web. Even a perfect experiment can't beat this. It's like trying to estimate the average of a population when you're only ever allowed one sample. Those two facts together mean something profound. Even with infinitely precise instruments, some aspects of the universe's global shape will remain uncertain. The error bars will never shrink to zero. You picture this as fog at the edges of a map. The central regions are clear. Coastlines and mountains are drawn with fine lines and vivid colors. But as you move outward, details fade, colors wash together, lines turn sketchy. It's not because the cartographer is lazy, it's because no one has been there yet, and perhaps no one ever can. Your cosmological map is like that. Near here and now, the laws are sharp, tested, precise. General relativity, particle physics, nuclear reactions in stars. On larger scales, curvature is constrained to be very small. Dark energy is measured to have a nearly constant negative pressure, but out near the horizon and beyond it, the lines blur. Maybe the universe is exactly flat and infinite. Maybe it's very slightly closed, curving back over unimaginable distances into a finite, edgeless whole. Maybe its topology is simple, or maybe space loops and twists in ways your current data can't reveal. The measurements you've heard about point strongly in certain directions, but they don't lock every door. And that's not a failure. That's part of the design. Science is often portrayed as a march toward final answers, but working cosmologists know it more as a dance with uncertainty. Each new satellite, each new survey, tightens some bounds and opens new questions. Planck sharpened the picture of curvature. Upcoming missions sharpen other pieces. But there will always be scales too large to probe, modes drowned by cosmic variance, distances forever out of reach. You might think that would be frustrating. Sometimes it is, but it can also be deeply calming. Because if the universe has built-in limits to knowability, then you're not personally failing when you can't wrap your head around the full truth. You're simply living inside a reality that leaves some things permanently in soft focus. Maybe the universe just loves to keep a little mystery for itself. You think back through the journey you've taken tonight. The ancient afterglow of the Big Bang, speckled with tiny temperature ripples, whispering nearly flat. Triangles on spheres and saddles, teaching you how curvature reveals itself in the sum of angles. Topological donuts and circles in the sky, hinting that space might loop in hidden ways. Inflation, smoothing and stretching, turning quantum jitters into the scaffolding of galaxies. Dark energy, quietly pushing the cosmic expansion into acceleration. Human eyes and minds, tiny and fragile, yet somehow capable of stitching all these clues into a coherent, if incomplete, picture. Taken together, these threads don't give you a perfect, final answer. They give you something more like a range, a family of universes consistent with what you see. Within that range, your own observable patch is almost perfectly flat, expanding, filled with structures spun from early fluctuations. Beyond that, the shape remains an open question, and maybe that's the right place to rest. Not in absolute certainty, and not in empty ignorance, but in a space where you know enough to feel at home and still have room to wonder. You can let the question itself become part of the lullaby. What if the universe is flat, stretching endlessly beyond your horizon? What if it curves gently back, finite yet without edges? What if space wraps and loops in topologies your brain can only sketch as donuts and spheres? What if this whole cosmic bubble is one of many, each with its own geometry and story? None of these possibilities changes the feel of the sheets against your skin, the weight of your body in the small gravity well of Earth, the rhythm of your breath tonight. They simply add depth to the darkness above you, turning the night sky from a backdrop into an active question. You are not required to answer that question before you sleep. You are only invited to hold it for a little while, the way you might hold a smooth stone in your hand, feeling its weight and coolness, without needing to know exactly where it came from. Wind down, about 300 words. Now, very gently, you can let the technical details drift to the edges of your awareness. Let omega S and LEs and FLRWs fade into a soft blur, like distant city lights seen through mist. Bring your attention back to simpler things. The feeling of the pillow under your head, supporting you, the way your shoulders sink just a little deeper into the mattress with each exhale, the quiet sounds around you, maybe a faint hum, or the distant murmur of traffic, or nothing at all but the soft rush of your own breathing. Above you, whether you see it or not, the universe goes on. Galaxies drift a tiny bit farther apart, stars burn, fuse, flicker, dark matter and dark energy do whatever they do, silently keeping the large-scale structure in motion. The cosmic microwave background continues to stream through the room, ancient photons passing right through you, unnoticed. You don't have to track any of it. You can simply rest inside it. You might imagine yourself as a small, warm glow on one arm of one galaxy, wrapped in layers of atmosphere and cloud and night. Around that glow, the universe stretches out in all directions, maybe flat, maybe curved, maybe more complex than you can say. But whatever its true shape, it holds you securely in this moment. The universe is still here, quietly working while you sleep. It doesn't need your attention to keep expanding. It doesn't need your effort to keep the laws of physics running smoothly. For a little while, you're allowed to hand everything back to the equations, to the stars, to the quiet machinery of space-time, and just rest. If thoughts about curvature or infinity drift back in, you can greet them kindly and let them go, like clouds crossing a dark, clear sky. They're part of the same universe that is already taking care of you, breathing you in and out as one small pattern in a much larger whole. Eventually, even the question, what is the true shape of the universe, can soften into something simpler. Here you are. Here is the night. Here is a cosmos, vast and mysterious, that you have touched with your mind. And now, it's okay to let that mind grow quiet and let sleep carry you through the curved or flat or looping fabric of another night.